and welcome to NPTEL MOOC on fiber optic communication systems and techniques. In this module, we will further study the basics of lasers, and if you recall what we studied in the last module, we saw that when you consider matter, which typically is a laser gain medium or the active medium as we would call it, this matter has different energy levels. They are separated by a certain gap in the energy levels. The reason why you have gaps is something that we are not going to cover in this course, but I will give you a brief idea when we talk about semiconductor basics in the upcoming module. But for now, just imagine that matter, whatever the active medium that we are dealing with, which of course is one of the first ingredients of what forms a complete laser. This particular active medium has multiple energy levels, or actually what it has are energy bands. And we consider two such energy bands, say E1 and E2, or since we are not going to overcomplicate ourselves, we will assume that instead of these bands being considered, we are considering the discrete energy levels. So, in that particular case, we can consider two discrete energy levels separated by a certain energy gap or a band gap, or in this case it would be energy gap, and in the equilibrium, and especially when the temperature is equal to 0 degree Kelvin, that is when there are no thermal energy available to the electrons in the matter, what you would find is that almost all of these electrons are located in the energy level E1, that is they occupy the energy states below that of the edge E1. And if you now assume that the temperature is actually greater than 0 degree Kelvin, then each electron has on an average a thermal energy of kT, which causes a few of the electrons to just get excited and land in the second energy level. Of course, as we have already seen, these electrons which have landed or atoms which have landed in general, they do not stay there for quite long, and they actually spontaneously come down from the higher energy level E2 to the lower energy level E1. And this interaction or if this reaction where the excited atoms or the excited electrons fall down spontaneously on their own without any intervention or without any external energy that is being supplied is called as the spontaneous emission, and this is one of the interaction that we have already spoken about. Of course, this excitation that has happened is also spontaneous in the sense that this excitation is not because of any external energy source, but the energy source coming simply because the matter is now at a non-zero temperature. So, this thermal energy which causes the electrons to just kind of go up or being excited into the next higher energy level also occurs spontaneously. So, you could in fact call this as kind of a spontaneous absorption, but this case spontaneous absorption of what? The spontaneous absorption of the thermal energy. But you see that it is not very convenient way of talking about it. So, we do not normally attribute any specific name for this interaction of electrons or atoms taking amount or absorbing a certain amount of kinetic thermal energy and then jumping up to the next energy level. But it is possible to actually excite atoms in a much more controlled way by having external pump signal. So, having an external pump signal allows these atoms in the ground state to actually absorb the energy coming from external energy source, which we call as the pump, which is typically optical signal or photons, or it could be simple current. So, both types are used in fiber optic communication systems to make different kinds of lasers. The one that is optically pumped is what is called as the erbium doped fiber, and you make a laser out of it. We call this as erbium doped fiber laser. But the semiconductor lasers do not really have an optical pumping, they have this electrical pumping. So, the idea is that you create certain amount of energy, or you actually supply certain amount of energy to the atoms which are in the ground state E1, so that when they absorb that energy, they can jump up to the higher energy state, or they can move to the next higher available energy state. And this process is called as absorption due to external pump being incident on the matter. Finally, when you have created sufficient number of excited electrons and all these electrons are essentially present in the form of excitation, very few of them start to drop on their own, okay, and how much of excited atoms drop spontaneously is proportional to a certain constant A times whatever the density of population that exists in the energy level E2. So, we call the density of population. So, as we have already seen the floor, ground floor and the first floor analogy in the previous module, you can think of simply this as the population density, the number of people, so to speak, each carrying the same amount of energy and located at the first floor, and when they randomly drop down and combine with the vacant space below, or they just go to the vacant space below, that is called as a spontaneous emission. Okay. So, of course, when they do so, they would actually emit a photon, okay, of an energy that is the difference between the two energy levels. So, the photon energy is hf, where h is the Planck's constant, and this energy that is emitted will be equal to the energy difference between the two levels E2 and E1. Okay. So, this spontaneous emission rate, that is the rate at which these atoms in the excited state fall down on their own, is kind of very small, okay, which means that most atoms do not, as soon as they land up on the higher energy level E2, they will not automatically drop down, okay, but they do drop down after a certain characteristic lifetime, which is proportional to the constant A. Incidentally, this constant A is called as Einstein's A coefficient, and it is really not a constant, it depends on several factors, but for our application or for our purposes, we will assume that this is to be a constant, okay, and this is called as Einstein's A coefficient, because it is the coefficient A, and this idea or this theory of what is called a semi-classical theory of radiation was first given by Einstein, and this is a very interesting and very simple ideas or simple way of tackling what happens with the when the radiation interacts with matter. Okay. Radiation, by radiation I mean optical energy. So, or it could also be the energy that is released in the form of photons by the lasing action itself. Okay. So, as we have seen, very few of them drop down by spontaneous emission, but when you now send in an external photon, okay, or it could be a photon that has been just generated with the noise, whose energy actually matches that of the energy difference E2 minus E1, then this photon will cause the electron here to drop down. Okay. So, this, and once it drops down, it of course emits another photon, okay, of the same energy hf, and it turns out that this new photon that has been emitted will, so this photon which has been incident is not actually absorbed, it is just used to trigger the excited atoms which are in the energy level E2 to drop down to E1, thereby releasing a photon. Therefore, after this first interaction, what you will actually see is that you have two photons which are identical in all aspects, and they have the same energy, they have the same polarization, and they have they are in coherence with respect to each other. Okay. So, you will actually see two photons. Now, these two photons go and trigger additional electrons or additional excited atoms which are present in the energy level E2, which will then fall down to generate a total of about 4 photons, right. So, you will now have, instead of 2 photons, you now have 4 photons, and as the external or as the noise induced initial photon kind of builds up, this process of emission continues to happen until all of the excited atoms in the energy level E2 have completely dropped down to E1, so as to give you a huge radiation. Okay. So, I am using this big arrow to indicate that the radiated energy or the number of photons that you are getting at the output or the optical power or intensity is quite high, and it is being stimulated in the sense that it needs of course some starting point of a photon which could be generated because of the noise, or it could be just kind of seeded from external sources, and once that has taken place, then the rest of the active material starts giving so many photons, because there is large amount of population at N2 because of the pump absorption, right. So, pump is incident, atoms at the ground level E1 absorb the pump photons and then jump to the excited state, thereby creating a population inversion here, that is the population N2 will be larger than the population N1. So, in equilibrium it is the other way around, right. So, in equilibrium, when there is no interaction going on, most of the atoms are in the ground level E1, but when there is external interaction going on in this form of pumping and subsequent absorption of the pump photons or the pump energy, then the number of atoms in the energy level E2 far exceed that of the atoms in N1, which of course is what we call as population inversion, and that is one of the key ingredient for a laser. So, once population inversion is achieved, then any small trigger kind of a thing, small in the sense that a very minute amount of initial seed photons are necessary to trigger this action, which causes or which builds up through the laser medium, and this process of building up a coherent radiation by continuously stimulated emission is in fact called as stimulated emission. That is, this is called as stimulated because it is being triggered by another photon, let us say. And how good are we going to absorb, or in other words, if I am supplying pump at density of phi of f, right, or maybe because I am actually looking at the pump photons, I am going to write this as phi p. So, if I am supplying a pump with a photon density, okay, which of course will be proportional to the intensity or the flux of the photon over the frequency interval f2 f plus delta f, because these quantities are actually frequency dependent. Okay. So, when I have this phi p of f df times hf, then that will actually correspond to the total energy density over the frequency range that we have considered, that is small f2 f plus df. In that range, whatever the energy density is actually proportional to the energy times the population, because each photon carries an energy of hf when you have a number of photons. So, this is the pump specifically, therefore, I am writing this as phi p of f, and that in the equilibrium or for a black body radiation is given by this expression, okay, in the sense that when there is an equilibrium achieved, then the radiation actually is quantized, and the radiation, quantized radiation, is given by this particular expression. So, now as the pump photons are incident onto the material causing the absorption to take place, what would be the rate at which the population density in the two levels actually change, right. So, remember, in the 0 degree Kelvin case, when there are no external energies, all of the atoms are in the energy level E1 itself, none of them are in the energy level N2. But we are not going to operate our laser materials or active medium in the 0 degree Kelvin situation, we will be operating them at room temperature, and because of the room temperature, there is a certain non-zero thermal energy available to the atoms, and these thermal energies are actually taken or absorbed by the atoms in the ground level, then they get excited into the energy level E2. But this process, because of thermal energy being absorbed, is not sustained, and the number of such excited atoms because of thermal absorption are actually quite small. Okay. So, in that room temperature also, most of the population is actually in N1, but once you start pumping in or sending the external pump, then this pump will give you energy, or pump gives the energy to the material, which then allows the atoms in the ground level E1 to absorb and move up to the next level E2, and when they do so, they are going to deplete the population N1 and increase the population N2. So, as pump photons are absorbed, N1 decreases while N2 increases. Okay. So, if you now concentrate only on two levels, E1, E2 with energy levels N1 and whatever initial energy level N2 that we have, and as the pumps are absorbed, the rate at which the population in the ground level is decreasing will be denoted by dN1 by dt, correct, and this will be because of three processes. Well, first it will be decreasing because you are sending in the pump, and the absorption process is given by B12 phi p df, okay, and I will put a minus sign here, the minus sign indicating that this is actually because of absorption, the energy or the population density in energy level E1 is decreasing. So, decreasing is represented by minus. Of course, this is the photon density, and B12, as you have guessed, is actually called as the Einstein's B coefficient. Of course, this is only telling you how the population density is being, or the pump photons are being absorbed, but how many actually leave the ground state N1 or ground state E1 is proportional to N1 itself. So, the expression that I have written in green color here, which is minus B12 phi p df n1, stands for absorption and contributes to decrease in the population level n1. Okay. So, you have minus B12 phi p df n1 causing the absorption process, but once they are electrons are at the top, okay, and because we have considered only 2 energy levels here, the same photons which have caused initial absorption can also cause photons to actually come down, that is they can cause the stimulated emission as well, but we will not write down that as a stimulated emission, we will simply write it down as stimulated emission, but the idea of stimulated emission is that they will increase the energy level N1, correct. So, that is they will increase the population level of energy state E1, and therefore, that that stimulated process can be written as plus B21. So, this would be B21, right. This is B21 where 21 stands for interaction from 2 to 1 or emission from level 2 to level 1. So, this would be B21, and of course, it is proportional to phi p df and whatever the population level that exists at N2. Okay. So, this is plus B21 phi p df N2, and of course, there is another term that we should not forget. The other term is the spontaneous emission term, right. Spontaneous emission term is, as we have seen, is simply proportional to A times N2, or in fact given by A N2, and it is N2 because it is spontaneously coming in from energy level E2. So, these are the 3 interactions on the right hand side which describe how the population density at E1 is changing. So, if you think of population density being decreased or increased as some sort of a current, then you can think of this equation that we have written as a Kirchhoff's current law, wherein the current here in this particular node will be given by outgoing current plus the incoming current. Okay. So, outgoing current is because of absorption, incoming current is because of the stimulated and spontaneous emission. Okay. So, we have written this equation, and I will leave as an exercise for you to write down an equation for N2. Okay. Again, be careful, any decrease in the population will be represented by a minus sign, any increase in the population will be represented by a plus sign, and for now consider only the 2 energy levels. Okay. I will tell you that only matters which have only 2 available energy levels will never allow laser to happen, or whether they will never allow lasing to happen. So, 2 levels are not good for lasers. Okay. So, 2 levels are not going to give you any laser. So, you need at least 3 levels, but most materials are 4 levels, but in some approximation one can think of them as 3 levels. So, in fact, the helium neon laser which operates at 632.8 nanometer, or the Nd:YAG laser which operates at 1064 nanometers, both these are 4 level lasers. Even the semiconductor injection laser diode is also a 4 level laser, but for some applications or for some with some simplifying assumptions, we can treat the 4 level systems as 3 level systems. Okay. So, 3 level gives you a nice, it is a minimum required level for lasing, and also is most applicable with some approximations of course for the more practical 4 level systems, and we will of course look at 3 level systems. But before that, the reason why I am considering only 2 energy levels is very simple. We have seen how the population densities look like when there is equilibrium or when there is no external energy being supplied in the form of a pump. In that case, we know that the population density N2 will be much less than the population density N1, and there is a relationship between these two which we have seen in the previous module. So, that relationship is an exponential relationship, right. Now, that we have some absorption and or we have some pump radiation being incident, and this we have allowed for stimulated, spontaneous and absorption, 3 different kinds of interaction with the radiation. What do you expect the relationship between B12, that is where the transition is from energy level E1 to energy level E2, and B21 where the transition is from E2 or energy level E2 to energy level E1, right. This is the stimulated emission, this is the stimulated or this is the absorption, right. So, what do you think of the 2 relationships, are they equal, are they different, is B12 smaller than B21 in magnitude, or B12 is greater than B21 in magnitude, and what is the relation with respect to A. All these relations can be obtained by reconsidering a situation where we are in the equilibrium, or I would actually call this as steady state. Okay. All that process of initially pumping in and absorption and all the things have happened, and now we have reached a steady state or an equilibrium. In the steady state, what happens is that there is a balance between absorption and emission. So, which means that the population density level dN1 by dt does not change, and in fact that would be equal to 0, that is the rate will be equal to 0. Okay. So, what it means is that all absorptions are balanced by emissions, one will be stimulated, one will be spontaneous. So, now if you set this dN1 by dt equal to 0 in the previous equation, that is in this equation, and then equate the terms, what you get is phi p df being equal to A21 N2 divided by B12 N1 minus B21 N2. So, please take this as a exercise in case you want to know how this equation is derived, and this equation is interesting because now what I am going to do is I am going to take this N1 out, so that I can write this as A21 N2 by N1, and then I have B12 minus B21 N2 by N1. But I know the ratio of N2 by N1. What is the ratio of N2 by N1? N2 by N1 is e to the power minus E2 minus E1, which of course is the energy gap, right. So, divided by KT, KT of course is the thermal energy. So, now I also know what is the energy density, right. So, that energy density was rho f df, and this was given by 8 pi hf cube df divided by c cube e to the power hf by kt minus 1. Of course, E2 minus E1 is equal to hf, so I can actually go and write that one in that form, right, and then equate this expression, okay, to the phi of x expression that we have written. So, this is of course equal to phi p of f df, okay, times hf. So, if you remove hf from both, then you will actually be able to write down the equation. Alternatively, substitute for phi p of f from the above equation, and then write down the equation here, and then equate the two. What you get is hf A21. So, sorry, I changed the notation here slightly. Instead of A, I have written it as A21, just to indicate that this is interaction from second or energy level E2 to E1. Okay. So, you have hf A21 by B21 df divided by B12 by B21 e to the power hf by kt minus 1. So, you can see that these two are essentially same, or equate the two terms out there, and what you will actually see is that B12 will be equal to B21, okay, because you look at the denominator here, sorry, this has to be in the bracket. So, you look at the equation here. So, you have e to the power hf by kt minus 1 multiplied by B12 by B21, and you have e to the power hf by kt minus 1, that would be B12 by B21. Therefore, we are led to a very important conclusion that the coefficients, Einstein coefficients of absorption is exactly equal to the Einstein's coefficient for stimulated emission. And then you have all this term hf A21 B21 df being equal to 8 pi hf cube df by c cube, and then you can equate the two to obtain A21 divided by B21, which is the ratio here, to be equal to 8 pi f square divided by c cube. Okay. So, I think there is a df, no, the df anyway will cancel. So, you have A21 by B21 being equal to 8 pi f square by c cube. Now, we are at the end of this module. So, what I am going to do is that I will ask you to calculate this ratio A21 by B21 for two different frequencies. One, the simple low frequency case. So, let us say a 50 kilohertz case, and then you increase the frequency to RF ranges or microwave range. So, let us say 3 gigahertz, and then you have and then you do the same thing for let us say about 200 terahertz. Okay. So, you are I will give you 3 frequencies, one is 50 kilohertz, the other one is about say 3 gigahertz. So, giga means 10 to the power 9, and then you do the same thing at 200 terahertz, tera being 10 to the power 12. Okay. So, we are increasing the order of magnitude in the frequencies here, and what you will actually observe is that this A21, okay, because it is proportional to the frequency square, increases as the frequency increases, and this is very important because at low frequencies, whenever you send in some light or shine light onto a matter, right, you are still giving some amount of energy, right, and then there is some movement from ground level to the other level if the particular matter supports that one, but the spontaneous emission is is so small in this case that you can completely ignore that. But spontaneous emission cannot be ignored when you start increasing to the frequency, say that 200 terahertz. 200 terahertz is roughly equal to 1550 nanometers, which is where you are operating in the fiber, you are operating with the optical fibers. So, to summarize what we have seen in this module, what we started off was by looking at the two population levels N1 and N2 belonging to the energy states E1 and E2. We saw 3 interactions: spontaneous, stimulated and absorption. We wrote down the rate equation. This equation where you see how the population density is changing is called as the rate equation. I will leave the rate equation for N2 to be written by you, and you can it will be essentially the same thing, but with minus signs replaced by plus signs. And then finally, when we equated the two under the steady state condition, we found a very interesting and very important conclusion that the coefficient B12, which takes atoms from energy level E1 to E2, is the same coefficient which takes atoms from E2 to E1. Okay. So, B12 is equal to B21, and finally, we also found out that spontaneous emission is proportional to frequency square and therefore increases as the frequency increases, and at optical frequencies, that is in a few terahertz scenario, this spontaneous emission will also become very important. What we will do in the next module is to apply these concepts and rate equation for a 3-level system, and then talk about how to actually make a laser. Thank you very much.